This is an introduction to our paper, NodeAwareSmoothing, Certified Robustness Against Graph Injection Attack. My name is Lena. Let me first introduce the background. In our paper, we mainly focus on node classification tasks, which have a wide applications. For example, in social network, node classification can predict attributes or labels for users, identifying influential individuals or detecting communities. And also in financial transaction network, node classification helps identify potentially fraudulent accounts or transactions. The most representative node classification model is graph neural network, known as GNNs. For every node, it aggregates the node features among its neighbors to make predictions. However, graph models are vulnerable to adversarial attack. As we all know, in computer vision, the panda can be misclassified if we add some noise to the image. This problem is also found in graph learning model. If we add or delete some edges on a graph, this graph modification attack can alter the results of node classification. To defend against potential adversarial attacks, researchers are dedicated to develop certified robustness. A classifier F is said to be certifiably robust for a given input if we guarantee that the classifier's prediction is unchanged within some perturbation sets around F. It is often an L2 number or L0 number. Robustness certification can also be regarded as a lower bound of the model accuracy under a given attack power. As the attack power increases, the model accuracy will decrease. However, no empirical attack can break the certified accuracy. Randomized smoothing is a general certifiably robust framework. Given an arbitrary classifier F, we can create a smooth model G. We first add some random noise to the input, and then the smooth model will return the majority vote for the noisy samples. The intuition behind this randomized smoothing is that with the random noise, the distribution of the perturbed data have some overlap with the clean data distribution. As long as the input is the same, the classifier F must have the same prediction. In this example, let's use the blue curve represent the distribution for clean data, and the red curve represent the distribution of perturbed data. We assume that the classifier F will return the class YA for the green area. And then we know that it also returns the class YA for the red area. As long as the overlap is large enough, we can guarantee that the prediction of the smooth model is unchanged. Despite the development of certified robustness, existing studies focus on defending against graph modification attack. The graph modification attack, GMA, it inserts or deletes edges among the existing nodes. For example, sparsely aware smoothing was designed to defend against GMA. When Xi denotes the existence of edges, it randomly inserts edge and deletes edge with a certain probability, P plus and P minus. Graph injection attack is another kind of attack that injects some new nodes into the graph and connect with existing nodes. Unfortunately, certifiably robust model against GIA remains largely unexplored. Our paper aimed to design an effective certifiably robust model against GIA. We propose node-aware bismoothing that tailors for GIA scenario. It is model agnostic and applicable to both evasion and poisoning attacks. Next, I will introduce node-aware bismoothing. First of all, let's formally define the GIA perturbation set as B rho tau G. Let rho denote the maximum number of nodes can be ejected by the attacker, and tau is the number of edges inserted by each inject node. The method of our provable defense is that for any node classifier F, we create a smooth classifier G. Our goal is then to verify whether the prediction of a given node V is consistent for all G points in the perturbation set. Our first attempt is to make adaptation from GIMA certificate. Firstly, we make a weak assumption on the node classifier. We assume that the isolated node will not impact the classification results of other nodes. This assumption is satisfied in most node classification models. With this assumption, we can pre-inject row isolated nodes into the graph. The row nodes can have arbitrary node features, and they won't affect the prediction of existing nodes. Then we can set p plus to 0 and p minus greater than 0. It means that we only randomly delete edges in the graph. Then we can certify whether the model can tolerate inserting arbitrary row tau edges. The certification is based on the condition that all inserted edges might be deleted during the randomization. However, the probability is very small. To increase the probability, a more suitable randomization is required. We notice that the inserted edges are all concentrated around the injecting nodes. So we introduce node-aware bismoothing. It randomly deletes the edges with probability PE, and it randomly deletes nodes with probability PN. Here, the meaning of deleting a node is to delete all its incident edges. The deleted node will become an isolated node. With this randomization, the probability of deleting all the inserted edges will be greatly increased. It means that our node-aware bismoothing can significantly increase the distribution overlap. The shadow in red is important for the certification. A larger overlap will lead to a larger certifiable radius. Next, let me briefly introduce the procedure of obtaining certified robustness. With node-aware bismoothing, we build a smooth classifier that returns the majority votes of random graph. In our paper, we have provided the certifying condition mu rho tau. If mu rho tau is greater than 0, then the prediction of smooth classifier is certifiably robust. To obtain the mu rho tau, we need to obtain the top class probability and the runner-up class probability, PA and PB. For defending against evasion GIA, we have a well-trained base classifier F. Firstly, we draw n random samples from randomization distribution phi G. Then, for n random graphs, we make n predictions, and then we count the frequency of each class. The upper bound and lower bound of probability can be obtained via Clopper-Pearson-Bernoulli confidence interval. Finally, we can get the certified prediction YA if the certifying condition is satisfied. For poisoning GRA, we use a similar procedure. The only difference is that we need to define a train and test classifier G. It is a model that trains on GI and then make predictions based on GI. For n random graphs, we need to train n models and then make the prediction. Note that the model should not train on any isolated node because of the assumption we mentioned previously. In our paper, we quantify and compare certified accuracy and average certifiable radius, ACR. Intuitively, the ACR is the discrete area under the certified accuracy curve. In the experiment, we observed that our node-aware bias-smoothing significantly outperformed the baseline. For poisoning GRA, we have introduced a variant on node-aware smoothing. The node-aware exclude. The exclude means that we exclude the isolated node from making prediction and voting. Because in poisoning setting, the model cannot train on isolated node. For this reason, exclude the isolated node from voting can increase the model accuracy. Our node-aware exclude model outperformed the baseline significantly. In the experiment of poisoning attack scenario, we set a number of random samples as 1,000. If we set a larger sample size, the certified accuracy can be further improved. Conclusion. This paper investigates the task of certifying graph-based classifier against graph injection attack GIA. We propose a novel node-aware bias-smoothing scheme that provides certificates specifically designed to defend against GIA under both evasion and poisoning threat models. Through extensive experiments on 3 datasets, we provide comprehensive benchmarks of our certified model against GRA. You might refer to our paper for more details. Thank you for your attention.